The next type of integral we'll talk about is integrals of rational functions and exponential functions. So a lot of this will be reviewed from the previous video, just a little bit of new stuff. So here's the type of integral we're going to try to evaluate in this video. It's going to be integral from negative infinity to infinity of p of x over q of x, so far the same as last time, and in addition multiplied by e to the I alpha x dx. So the new addition here is this e to the I alpha x, that's the exponential function. So the other restriction is that alpha should be positive. We'll talk about being alpha negative at the end of the video. And addition to that, all the same conditions on p and q as the previous video. And just to recap what those are, that is that p and q are polynomials, which are real valued on the real axis. Also, degree of q is greater than or equal to degree of p plus 2. Q of x is not equal to 0 for all real x. Okay, so if all those are met for p and q, then we can go ahead and use this method. So the contour, or the curve we're going to use, which I said was the hardest part of all these integrals, finding the right curve. In this case, we're going to use the same exact curve. We're going to be making it the upper half plane, and we're going to be starting with this semicircle. So it's going to be the semicircle starting at negative r, going to positive r, and then going on this semicircular loop of radius r back to this negative r. So it's like that. And now this whole curve right here, this whole curve we're going to call gamma sub r, and just the semicircular part we're going to call gamma sub c. So I said note on gamma sub c, y is always positive. So keep in mind that this gamma sub c does not include any part of this real axis. It's purely above the real axis. Okay. So next thing we want to do is we're going to write the integral, and this integral right here can be broken into two parts. So the integral on the line from here to here and here to here. So the integral of p of z over q of z e to the I alpha z dz over gamma sub r can be broken up as integral from negative r to r p of x over q of x e to the I alpha x dx. Notice they're all x's now because it's the real axis. And this is the integral we're interested in, right, as when these r become infinity. But also we have to add to that the integral on gamma sub c, right, because that's the other part of this curve. The integral on gamma sub c p of z over q of z e to the I alpha z dz. And I put a green asterisk here because we're going to use estimations to try to figure that out. But before we do that, let's talk a little bit about e to the I alpha z and the modulus of that, which is, we're going to use that also in the estimate. So the modulus of e to the I alpha z is the same thing as the modulus of e to the I alpha x plus iy, because we said z is x plus iy. And now we can split this up. Using our rules of exponents, we can split this up as integral, the modulus of e to the I alpha x times e to the negative alpha y. Okay, so this is simply just done by, you do e to the I alpha x plus, and then this I alpha and this iy become a negative alpha y. It's negative alpha y. And then simply you get e to the I alpha x and e to the negative alpha y. Okay, now you can split this up into two separate integrals, because we said if we have a multiplication and a modulus of the whole thing, you can just take the modulus of each separate part. So we're going to take the modulus of this part and the modulus of the next part. So the modulus of e to the I alpha x is what? Well, we put it down here. It's going to be cosine alpha x plus I sine alpha x. That's what e to the I alpha x is, correct? And if we take the modulus of cosine alpha x plus I sine alpha x, we get 1, because it's cosine squared this plus sine squared this. So it's going to be 1. And the modulus of e to the negative alpha y, what do we know about e to the negative alpha y? Well, it's a purely real number, because alpha is real. We said its alpha is greater than 0. And y is a real number. So e to the negative alpha y is also a real number. So it's this modulus times this modulus is simply equal to e to the negative alpha y. And we took it out of the modulus, because if you take the modulus of a real number that's positive, keep in mind, e to the any real number is positive, then you can just take it out of the modulus. So then we have times 1, because this e to the negative I alpha x modulus was 1. And now this whole quantity right here is less than 1. And why is that? A is positive, or alpha is positive, and y is positive, which means e to the negative alpha y is e to some negative power. And when we have e to some negative power, it's going to be 1 over e to some positive power. And that positive power will be greater than 1. Therefore, 1 over something greater than 1 is going to be less than or equal to 1. So we have that e to the negative alpha y is less than or equal to 1. Okay, now we're ready to carry out the estimation, and it's not that bad. So we're trying to estimate this integral right here with the asterisk next to it. And we put that, and it's going to be less than or equal to the maximum value of the integrand, the modulus of the integrand on that circular arc, times the length of the arc, which we know is pi r, because it's 2 pi r divided by 2, so it's going to be pi r. Now the last thing to do is try to figure out the maximum value of this. So we want to find what this is less than or equal to. So this, from the previous video, if you remember, we already have an estimation for p of z over q of z. It's c pi over r. And now we have a new estimate for e to the I alpha z. So we said that e to the I alpha z modulus is less than or equal to 1. So we can just put 1 right there. And we're just left with c pi over r. And as r approaches infinity, which means as the circle gets bigger and bigger and bigger and approaches the entire upper half plane, then we have c pi over r simply approaches 0. So again, we found that this integral right here approaches 0 as r approaches infinity, which means that we can just pretty much cross it out, and this integral here is simply equal to this integral here as r gets very, very big. So we've written down here the integral of gamma sub r p of z over q of z e to the I alpha z dz is equal to 2 pi I, the sum of the residues of p over q e to the I alpha z at the isolated singularities z sub k, where these lie in the upper half plane. So I put a u under the summation sign, and u just implies that these z sub k should come from the upper half plane only. And this also equals, as we just found up here, the integral from negative infinity to infinity p over q e to the I alpha z dz. And why are these infinities now? So this is a negative infinity and positive infinity because this r and this negative r and r go to infinity, and that's how we got the estimate of this to go to 0. So we simply have this formula. We have that this integral that this overall integral is equal to the sum of the residues times 2 pi I, and that's equal to the integral that we're interested in evaluating. So if we want to evaluate integral, we just have to find 2 pi I times the sum of the residues of this function in the upper half plane. Okay, let's do an example. So here I have an example. So we are trying to evaluate this integral right here. So we want to evaluate the integral negative infinity to infinity e to the I alpha x over x squared plus x plus 1 dx. Now notice something. This does not have to be real, right? Because this has a e to the I alpha x. This has an I right here. So it doesn't necessarily have to be a real integral in the end. We'll find that it's actually not. So first thing to do is identify the p of z, which is 1. Q of z is the denominator. And we have this e to the I alpha x or e to the I alpha z as we had before. Okay, so now we have to find when q is 0. When is the denominator 0? So we can isolate the we can find the isolated singularities. Well, since it's a quadratic, we can solve using quadratic formula, and we get two roots. We get negative 1 plus I rad 3 over 2 and negative 1 minus I rad 3 over 2. Now, which of these is in the upper half plane? We find that z1 is in the upper half plane and z2 is in the lower half plane, which means we don't need to worry about z2 at all. We're just going to be worried about z1 in the upper half plane. So the answer to our problem is actually 2 pi I times the residue of our function, of our integrand, at that point, at negative I plus negative 1 plus I rad 3 over 2. Okay, so the next thing is to just evaluate this residue, and once we do that, we'll be done. So we want to find this residue right here. So how are we going to do that? Well, we're going to use the same quotient residue rule that we found in the in computing residues video. So we have a of z is going to be the numerator. It's going to be e to the I alpha z. Okay, b of z will be the denominator. It's z squared plus z plus 1. Okay, and we have that a of z is analytic on u, or the upper half plane, and b of z, we have b of this number right here, b of negative 1 plus I rad 3 over 2 is equal to 0, but b prime of that number is not equal to 0. So all these conditions are met. We can just go ahead and plug in the residue formula. So the formula was that the residue is equal to a of that number over b prime of that number, and a of that number comes out to e to the I alpha negative 1 plus I rad 3 over 2, and b prime of that number comes out to I radical 3. So now we multiply this by 2 pi I, because that's what the residue theorem tells us we should do. And once we do that, once we do 2 pi I times this, we see these two i's cancel out. But we still do have an I up here, which is okay, because if it's an imaginary integral, then it's fine, because we expect that it's possible to be imaginary. Okay, so we just have 2 pi over radical 3. So this should be a radical 3 right here. 2 pi over radical 3 times e to the I alpha negative 1 plus I rad 3 over 2. Okay, so that's the answer to that. And the last thing I want to talk about is what you should do if you have this integral, and the only thing that changes is that you have a negative sign right here. So alpha is still positive. It's just that now the exponent on top of e is negative. So in that case, you're going to follow this exact same procedure, do this estimate, but instead of using this contour in the beginning, this curve, the curve you'll be using is going to be in the lower half plane. And it's going to look like this. It's going to start at negative r, go over here, and come back down like this. And it's going to follow this direction. Now be wary, because this is the negative orientation, whereas this orange curve was the positive orientation for this curve. Now we have the negative orientation. So make sure you put the negative signs in the right places, and otherwise use this bottom lower half plane. So now you're doing residues that are in the lower half plane, not in the upper half plane, and you'll get a similar formula. So that's how you do that case.